So as promised, we will now show that we're indeed achieving this approximation ratio. So the analysis is actually relatively simple, but neat. So we're proving things. Now, Lambert's W function is defined as follows. So it is the function that satisfies the condition that k times wk is equal to e to the power of wk. So it should be nothing special for you, because if you get a function that is defined as follows, that k is equal to the function e to f of k, this is nothing else than defining the logarithm, right? So here the only difference is that we're putting f of k also here. So this is so this function clearly has to be growing more slowly than logarithm. So this is what Lambert's W function is, and we only learned about this after it turned out that we need to use it in the algorithm. And now this algorithm proceeds in rounds. So let ni be the number of unassigned agents after round I. Okay, I guess I need a volunteer again.
Is it one function or a family of functions?
So if you look at real values and values above some, I guess above 0, then there's a branch that is unique. If you go into complex numbers, you get several branches. But in the world of real numbers, as we're looking at them, it is unique. Okay, so
Agents are voters.
yeah. So the word agent and voter is essentially the same in this literature. Yours?
I'm volunteering.
Oh, volunteer. Okay, good. So we have ni unassigned agents after round I. So the algorithm, just to make a visual for it. So of course we're the way you can look at it is that we have this profile V1 through Vn. There's this line of cutoff, and after round I, there's a bunch of guys Ni who are still unassigned. So here, of course, I'm sorting so that the assigned guys are on top, Ni of them are still left. Now I claim that the number of unassigned guys is at most n times minus wk over k to the power of I. So repeating it, Ni is smaller or equal to n times 1 minus wk over k to the ith power. So I mean, it's the same thing as here. I'm just somehow writing it so you have time to digest.
So we will not change k to k minus 1.
K to k minus 1, why?
Because we already take one person.
Oh no. So yes. So this wk. So this is after ith round. So in fact we have already taken I persons.
Okay.
But this will not change. It's always k, the original committee size. Okay, and you can also see that this, of course, it works for 0, because n0 means after round 0. So in fact, before you start the algorithm, it is smaller or equal to n to the power of 0. So n times the expression to the power of 0. So it's n smaller than n, perfectly fine. Now. We're claiming that there is a candidate ranked among top x positions by at least ni x over m agents, by the pigeonhole principle. So here we have x positions by definition, and so actually I should maybe write it here. Here there is x positions, right? Because only top X positions matters. And here we have Ni. So the area of this square is simply Ni times X, right? Now imagine that you're putting their candidates. So if you divide by m, this is the, if you take kind of the highest number of times a candidate appears here, and you want to minimize it, then the best you can achieve is nix divided by m. So this is the pigeonhole principle. Right?
M is the number of remaining.
M is the number of all the candidates. Actually, you could even have m minus I here, but it's not important. Okay, so
So the worst case in which sense?
essentially, so we were in the I plus first iteration, we're going to pick someone who appears in this square the largest number of times. So we want to somehow be against the algorithm. So we're wondering what is the smallest number such that the most frequent candidate appears.
So all, all evenly.
Yes. So the answer is when they're split evenly. Okay. So there is a candidate ranked among top X positions, ranked there by at least this number of agents, and this means that the number of assigned unassigned voters in round plus first is the number of guys that were already unassigned minus at exactly this value from the pigeonhole principle, because we know that we will assign at least this many. Okay, and what you get is so you have this ni minus nix over m. So you take ni in front of the equation, so you have 1 minus x over m. But x is in fact m times wk over k. So if you divide it by m, you simply get ni times 1 minus wk over k. Okay? But now, by the inductive assumption, you know that ni was already smaller than n times this value. So this is smaller than n times 1 minus wk over k to the ith power and multiplied again by the same expression plus 1. So this way we get our inductive step. Okay? So this claim our proofs. This proves our claim. And doubts?
Could you repeat like the intuition behind the claim?
The intuition. I'm not sure if I have one, but the best I can give you is so initially at round 0, so when you take I equal to 0, after round 0, so in fact after doing nothing, n0 is smaller or equal than n, which is perfectly true because the number of unassigned agents is, well, n, right? So then in the next round, this area is quite big. So the candidate that was appearing there had to be there many. So the candidate that was most frequent here had to be there many times. So in the first iteration, we're covering a lot. Then we're covering a bit less and less and less, like that. And this is captured by this claim. So you can see that the number of unassigned voters is actually decreasing exponentially, because wk over k is less than 1, right? So 1 minus wk over k is less than 1 as well. So this is some value that will decrease exponentially. So in the first round we decrease by some number of positions, and then a bit less, a bit less, a bit less, and so on. So is that good enough? And I guess, is the math acceptable? Okay. So we have proved our claim. So in particular, the reason why we have done it is that we can estimate the value nk. Nk is the number of guys without a representative after the kth round. So nk is n minus wk over k to the power of k. Okay, that's just applying the claim. Then what I'm doing here is, here was power of k, I change it to the power of k over wk, and I once again, in the big brackets, take it to the power of wk. So this is simple equality. This is nothing special. However, now here you have 1 minus wk over k, and here you have k over wk. So as you probably know, if you have an expression of the form 1 minus 1 over x to the power of x, then this is somehow approaching 1 over e as x becomes larger. And it's approaching it from so that you have inequality such that you can replace this expression with 1 over e. So you have n times 1 over e to the power wk, and this is exactly the moment where we're using the definition of wk. So what we have here is, okay, I need some more clean board. So we know that k is equal to wk e to the power of wk. What we have there is 1 over e to the power of wk. So this is the same as k over wk is equal to e over wk, right? And if we now inverse, then wk over k is equal to 1 over e to the power of wk. Okay, this was just definition of the Lambert's function. And this means that this 1 over e to the wk we can replace with wk over k. So that's why we get, okay, so this way we got an estimate on the number of people who are somehow left without a good candidate after k rounds. And this is enough for us to get the approximation ratio that we wanted, because the final bound on the utility, which here is score, is I'm simply saying that, I shouldn't actually have cleared that part, but oh well. So if we have our profile and the top x positions are where the guys were selected, we have number of candidates minus x is the lowest possible score that our selected guys can have, right? Now n minus n over k is the number of guys who definitely have a representative, because we had at most nk here, so this must be n minus nk. Okay, so that's easy enough. Now m minus x, okay, let's do it slowly. What we have is m minus x times n minus nk, and this is equal to, now m minus x, it is m minus m wk over k times n minus, and this is of the same shape, nwk over k, nwk over k. And now we can take m in front of the bracket, take n in front of the bracket. We get n times m. And what is left is m minus wk over k squared, because it comes from both places. And of course, this is greater or equal n times m minus 1. The m minus 1 I'm simply doing for beauty. And 1 minus 2 times wk over k. And I could add plus w square k over k square, but it's only increasing, so I don't have to, and I decided not to bother with it. So I just finished here, because I can bound like this. And this gives me exactly the bound I wanted. So, are you happy?
Yeah, there's just one equal instead of the first equality.
No, this is, oh yes, well, no, this is equality. Why not?
K is small.
Is gone.
Oh, sure, okay, in that sense, yes. Okay, sure. So, yes. Sure. Okay, so this way we have shown that this algorithm actually has an incredibly good approximation ratio. Yeah?
I have only one question. Was it easy to understand that x should be this formula?
So I think we started with a few other things. And I think eventually the idea was, okay, it must be some function. So let's just go with it. And when we reach this point of calculations, okay, this should be a function that has this property, that it is like this. And then, oh, actually this has a name, even better. So this really kind of came up from the analysis. Okay, so we're happy with, so this algorithm, so we thought it was kind of a success, because really in most settings, we get very high approximation ratio. So in fact, this is how this big function, our approximation looks like, depending on the committee size. So for committee size 1000, we're nearly perfect. And even with relatively, like committee size 100, we're above 90%. So remember, greedy algorithm, 63% guarantee. We're doing, at committee size 100, we're already above 90%. Quite a success. Until we actually run it. Because here's our, so when we run it, okay, the first committee size 1, here, okay, could have happened. Committee size 4, this whole area is completely abandoned, and it doesn't have to be. Larger committee, again, nothing here, here a big hole, but somehow constant. Here, again, big hole in the center. It's, I mean, if we increase enough, it actually looks nice. But if you have enough candidates, it's really not so difficult to be good. So the question was, what happened? How come a 63% approximation ratio algorithm gave much nicer results than a 90% approximation ratio algorithm? Well, the answer was simple. The 63% greedy algorithm was actually achieving like 95% approximation ratio on this data. It is just a lower bound. And interestingly, when we, again, so this was actual Chambering Courant, this was the greedy algorithm, which was clearly biased. What we achieved now is simply a different kind of bias, right? Because here, most winners were in the center, whereas they should be nicely spread. Here, there's still some in the center, and there are other concentration points, and we still have some distribution. So, okay, in terms of mathematics, a great success. In terms of doing it for avoiding bias, well, not so much. So, what would you do to improve this algorithm? So of course, we've done nice mathematics to show approximation ratio, but what can you do to actually make it work in practice?
So Alexei proposed iteration for previous greedy method, but that would also work here.
So.
Okay, so you select the top guy,
Mm-hmm.
and then you select the second,
Mm-hmm.
and then you wonder if after selecting the top guy you want to reconsider because you already.
Mm-hmm.
Or let me start from. So you select the top guy, you still don't cross this water cycle.
Mm-hmm.
You select the second guy.
Okay.
Okay, and then you cross one.
So you can do this at the last step or
Mhm.
on each step. So if you have a committee of size K,
Mm-hmm.
you just check can you replace one of
Okay.
these members to another and increase your
Okay.
function. So it is linear on this step.
Sure. That's not such a bad idea. We'll actually see something along these lines. But here, there's a much simpler solution.
Move X.
Move X? Who said that? Exactly. This is, it turns out that, so, okay, historically what happened, so, okay, we run it for this value of X, okay, doesn't work so great. Let's make it 2X. It works well. Oh, but only in this example. Let's make it 3X. On another example, it works well. Let's try every X and take the best committee we computed. And then, if we just run the same algorithm for every possible value of X, so it's multiplying the running time by a factor of M, and the result is we're starting with the center, committee of size 4. So somehow it worked like magic. So you can see this is actually really beautifully covering with all the candidates given. And more importantly, when we go to the histograms, they actually almost perfectly copy the original histograms. So for a long time, at least for a few years, this is how engineering defeated mathematics. Because, okay, we can play with this X value, but why? And eventually we finally understood what was happening there. The thing is that the way where you put the X value actually implies the ratio between the largest, the biggest group. So the first voters selected, they're guaranteed to have some number of, the first candidate selected is guaranteed to represent some number of voters. The last one is guaranteed the smallest one. And the ratio between these is somehow characteristic of the preference profile. And it turns out that this ratio between the largest and smallest group was different than the actual theoretically chosen X. So to actually match algorithm with the data, we had to change the value of X. Okay, was there a question or just? No, okay. Okay, so this way we achieved actually a really good approximation algorithm, polynomial time approximation for Chamberlain-Courant for the case of Borda. But what happens with approval? So actually, maybe this is a bit unfortunate, but the last session starts with 2 proofs. So now we'll have another proof and another algorithm dealing with Chamberlain-Courant this time. So we know that we have NP hardness, we know we have W2 hardness, and the 1 minus 1 over E approximation bound, the 63% greedy algorithm, we know from submodular optimization that it still works because the function in the approval setting is still submodular and it's still monotone. So this holds. The problem is that it's actually impossible to find a better approximation algorithm in polynomial time unless P is equal NP. So we don't expect P to be equal NP. It was actually a quite important result regarding set cover problem that showed that this is essentially impossible to beat. You cannot do better in polynomial time, that's it. So what we decided to do is consider parameterization by the committee size. So we're back to the FPT and parameterized algorithms. And we knew that for committee size, we have W2 hardness. So it's difficult so it's impossible, for all we know, to have an FPT algorithms parameterized by this value, but at least maybe we can have an approximation algorithm. And it turned out that indeed we can. So in spite of this W2 hardness, but there's one more caveat. We have to assume that each voter approves at most P candidates, where P is a constant. So not even a parameter, I think. Maybe it could be a parameter, but it must be, but let's say a constant. And this is not so bad, because in many elections, you could say, you're only allowed to vote for 5 people or for some number. So, but if you have that, then we will have an algorithm. And algorithm 1, whose analysis I will not show you, it's maybe not so complicated, but it takes some work as well, simply says, take this strange number of candidates that are most frequently approved. So take a group with the highest approval numbers and try simply brute force all committees among these, output the best one, and this finds a beta approximation algorithm for the approval setting. So this is somehow a smart brute force over a limited set of data, but it's looking among the most approved candidates. And it's not so intuitive why there, but it actually works. Okay, so the algorithm that I will show you is actually dealing with the following case. What if we want to not maximize the number of guys that are happy, but what if we want to minimize the number of voters without a representative? So we're essentially just taking a dual of our goal function. Instead of maximizing the satisfaction, we're minimizing unhappiness. Okay? And in this case, a simple search tree algorithm works. And the search tree is as follows. Choose a voter without a representative, randomly. He will have only P sub places to branch through because he's approving only of P candidates. And just take the best you can find. So I will first try to show you an example of how this algorithm proceeds. So imagine this is our profile. Or you don't have to imagine because this is simply our profile. Now, the way the algorithm works, it's first it says choose a voter without a representative randomly. So I randomly chose W2. Okay, W2 is approving of 3 candidates, red, violet, and green. So I have 3 possible options that I can branch on. Huh? Yeah, this should be green, sorry. And let's say I'm first branching towards red. Okay, if I'm branching towards red, then everyone who already had approved of red is satisfied. And I'm choosing random voter, in this case V3. I have 2 choices. Let's say I choose blue. If I choose blue, I go there. I happen to satisfy everyone. So normally in this algorithm, at this point, I would simply finish. I would simply claim, okay, this is done. But if the algorithm continued, it would go to yellow, it would try yellow, okay, then we have all but one, then it would branch back, go to violet, okay, do violet, then choose random voter V1 in this case, choose something, and proceed like this. So in fact, if your goal was to check if you can cover every voter, this would be a simple, then even without randomization, this would be an FPT algorithm, right? Because you have to make committee of size k, so the number of steps branches down is k. In each time you make p choices, so it's p to the power of k choices that you need to make. Okay, right? So the only difficult part is that in fact we cannot be sure that we will actually satisfy everyone. We just want to minimize the number of people who are not satisfied, and that's why we have to make these choices of voters randomized, and we have to ensure that we actually achieve a good approximation ratio. So why does it work? Why does it actually achieve the effect? So the intuition is, as I told you, if there is a solution that gives a representative to every voter, then that algorithm will find it. And if there is no such a solution, it will find something good. Okay, so now the analysis. So let P be the probability of finding a beta approximate solution. Okay, by beta approximate, this is a minimizing problem, remember. Okay, let C star be an optimal committee. So a committee that leaves as few people uncovered as possible. Let N star be a set of voters who have representatives under C star. Okay? And finally, U star are voters who do not have representatives under C star. So essentially, the set of all voters is N star union U star. You either have a representative or you don't. And this is the optimal committee. Okay. So consider some node in this search tree. So you are somewhere here. And let X be the voters without representatives at this node in the tree. Okay? You can be there. These guys do not have representative. Now, if fewer than beta minus 1 over beta fraction of X belongs to N star, we'll try to think of something. Okay, so X are guys without representatives, N are guys who have representatives under C star. So less than beta minus 1 over beta is actually not so nice, because if the proportion of guys from X who belong to N star was high, then we could just randomly choose a voter from X. We would nearly certainly try a voter who has a representative in C star, and then of course we would try this representative and we would add the representative to the committee. So this is actually a difficult case for the algorithm. Okay, so less than beta minus 1 over beta fraction of X belongs to N star, but this means that more than 1 over beta of X belongs to U star, right? Because if they're not in one, they have to be in the other.
So if it is bigger than beta, or what?
If it's bigger, then essentially, then we'll show that we can do nice things. But for now, it's less. Okay? So more than 1 minus 1 over beta X belongs to U star. And this actually has a funny consequence, because if more than this many belongs to U star, then certainly 1 over beta times X has to be smaller than U star. Because if more than this many guys belong to U star, then at least this has to be smaller than U star, so they all fit in. Yeah? Right? But then, simply by a simple multiplication by beta, you get X is smaller than beta U star. So voters without representatives at some node in the tree, there's less than beta times U star of them. It's a minimization problem, so beta is larger than 1. So this is exactly our approximation ratio. It means that if we ever end up in a situation when at some point in the computation this is not satisfied, this means we have already definitely found our approximate solution, our beta approximate solution. So this means that we can assume that in every node it is always the case that more than beta minus 1 over beta fraction of X belongs to N star. Okay? And this means that probability of computing an optimal committee is actually beta minus 1 over beta to the power of k. Why is that the case? Because in every step we have, so X are voters without representatives at some node in the tree. N star are voters who have representatives under C star. So with probability beta minus 1 over beta, I will randomly choose a voter among those in X who is in N star. When I randomly choose a voter from N star, it means that, so I will branch into all possible, all candidates that he approves of, and in particular he approves the committee member in the optimal solution. So I will definitely choose the guy from the optimal solution, and then I will branch again. And I will go into the computation. And then again, with probability beta minus 1 over beta, I will once again choose someone who is satisfied in the committee, who is satisfied under the optimal solution. I will choose the guy from the committee for him, and this way I will recreate the optimal solution with probability beta minus 1 over beta to the power of k. The power of k comes from the fact that I'm doing it over k steps in the path. Okay? Is it unclear?
So is P the probability that's one path in the tree?
So P is the probability of finding a beta approximate solution by running this algorithm.
But is the expected one path in the tree or
So I'm going over the whole tree.
Yes.
So for a single run of the algorithm, I'm doing the whole tree, but the randomness is over the choice of the voters.
Yes.
Mm-hmm. Right. So this is an exponential time algorithm in terms of P and K. And also the probability that it succeeds is somehow exponentially small. However, if I repeat beta over beta minus 1 to the power of k times this algorithm, then it's simple probabilistic analysis that you can show that it reaches some high probability. If you multiply this by 100 times, then you have near certainty that this algorithm will succeed. So it's exponential both in the probability that you want to, or the approximation ratio you're aiming, because beta is the approximation ratio you want to get, and in number of the committee size k and the number of approved guys p. But beta is considered to be a constant, p we assume to be a constant, and k is our parameter. So this is an FPT approximation scheme. Have we ever used it in practice? Not a chance, because of course it is way too slow for any practical application, but it's still a nice theoretical result. Okay? So are we happy? I'm quite happy.
Is that a big number?
Is beta a big number?
And now the number of trials.
Oh yes, it's beta over beta minus 1 to the power of k. So it's pretty large, because it's growing.
It's like hundreds, thousands.
So beta is, for example, beta should be a number close to 1 to get a better approximation. So if you want a 2 approximation, so it's possible that, imagine that there's a problem with 1,000 voters where 100 voters are left unsatisfied in the optimal solution. If you take beta 2, it means you're allowed to have 200 unsatisfied voters. But if you take beta 2, then beta over beta minus 1 is 2 over 1. This is 2. If your committee size is 10, then this is already 1,000 trials of an exponential time algorithm. So it can grow quite fast. So if you want, if you would take beta equal 1.5, you would have 1.5 over half, so 3. Now you have 3 to the power of k. So the closer to 1 you are, the more trials you need to run, but the higher approximation ratio, the better approximation ratio. Okay. So we move on. And there's lots of other ways of solving computing Chamberlain courant. You can run a Metropolis algorithm, which means essentially simulated annealing. And this is actually somehow your idea. So your idea was that when you have a committee, you can simply take one committee member, try to replace him, and put someone else. In fact, simulated annealing works exactly like that, with small addition of randomness. So you just start with a random committee, and then you choose a random committee member, throw him out, put a new guy in, maybe also chosen randomly, and check if this committee is better or not. If it's better, you just keep it like that. If it's worse, then you keep it with some probability. And you repeat that for many iterations. It's amazingly efficient. It's about as good as the algorithm P, and it's a great way of solving this in practice, provided you don't need guarantees. So algorithm P gives you guarantees, other solutions give you guarantees. Simulated annealing gives you nothing, it just gives you good committee. Which is good if you're running in business settings and is unacceptable if you're running it in politics. so I mentioned that there was this variant of greedy algorithm with different way of choosing the candidate. This works as well. And also, somehow along your line of thinking, you can simply use clustering to compute Chamberlain Courant. So the way it works, so we're using Borda Chamberlain Courant to cluster voters. And in fact, I will just show you the pictures because this is somehow explains the idea best. So we're starting with a preference profile. We have some initial committee. We can choose it randomly, or we can compute it by greedy CC, or just somehow we have it. And we're starting with this committee, and it turns out that here red is better than orange in all these votes, and orange is better than red in these votes. Okay? Now in each of these elections, we can run a single winner Borda election. So here Borda winner is the pink, so pink lady is the Borda winner of this election. Here of course orange because there's just one voter. Okay, but these guys make up a new committee. So we put them in a committee and we partition here pink lady is better than orange, here orange is better than pink lady. Okay, nice. Find Borda winner in each. Here of course it's pink lady.
How we constructed this separation again?
Okay, so we are here. We computed here Borda winner is pink lady. Here it's orange guy. Now if you look at this, pink lady is better than orange guy in these votes. Whereas orange guy is better than pink lady in the remaining ones. So that's how I create the separation. Now I'm running Borda election again. Pink lady of course wins here. This will not change, but here the red guy wins. So again, I change the committee. I compute the winners. Now it's pink lady here, red guy here. I found a very good committee. Okay? So this way the clustering approach works. There are some comments how you can make it even better, but the interesting thing is it's essentially 99% accuracy. It's near perfect solutions if we do it well. So if we mix all our ideas, we get practically perfect solutions. Okay. So the summary of this diversity coverage part is there are many applications, such as facility locations, choosing movies on the plane or whatever else. Chamberlain Courant indeed seems to be pretty good for this coverage thing, and this is confirmed both by axioms and by experiments. And finally, it's NP hard, but there are lots of ways to deal with this difficulty. Okay, so the last big section of this part is proportionality. So as I told you, we have actually a choice. We can either go into proportionality, or we can try to jump back to where we stopped yesterday.
Do you recall where we stopped yesterday?
Excuse me?
Would you recall where we stopped yesterday?
Oh, I know where we stopped yesterday. Yes, we stopped at this Borda shift bribery to approximation algorithms. So essentially the choice is between, we can either continue with multi-winner elections and go into the world of proportionality, or we can go back to single winner elections and we can continue with various algorithms for cheating in elections and dealing with that.
Let's vote.
Yes, let's vote.
Proportionality, ребят.
So who wants proportionality?
Proportionality.
Okay, that looks like a majority vote, but who wants non-proportionality? Okay, so 3-4. That's tough, but.
What did you choose?
Huh? Well, I mean, I can do either.
We should deploy some of material to the study.
That's true. Yes.
It's proportional.
All right. I was wondering if we could even split this in halves, but that would be even worse. So in some sense, I'm not even sure what I prefer because this fits naturally, but the proportionality slides were done by my co-author, and I did them once and I only succeeded so well, so we'll see. Okay, but we're moving to the idea of proportionality. And we want to choose a committee that represents the voters in proportional way. And so this is somehow a completely different setting than individual excellence and than diversity that we have seen so far. This will be, again, a bit less algorithmic, a bit more, actually there are some algorithms. So one of the simple solutions for proportionality, and this is in fact what is done in, for example, in United Kingdom, is says, okay, let's divide the country into single-member districts, and in each district we run a single winner election. So of course the problem is that you might have districts like this, and even though each of them seems pretty mixed, you have here 5 green candidates, but only so 5 green voters, 4 red and 4 orange. Here 5 green, 4 red, 4 orange, 5 green, 4, and so on. So clearly, this is not a very proportional result, even though the country is split nearly 1/3, 1/3, 1/3, but there is this small advantage of the green voters. So, in fact, we have a completely non-proportional result from using single winner districts. In fact, if you think about it, it's possible that with 25% of support in the country, you can form a majority government. Because it's enough that in just one district plus half, you have half plus 1 support, and that's about 25%. So single winner, single member districts, not such a great idea if you're definitely after proportionality. Of course, they don't work so badly, even though England has some problems with them. Because usually countries are not so, somehow, they're more mixed. I mean, they're not so heterogeneous. Okay. But from our purposes, this is simply not proportional. So what is otherwise done in many countries, in particularly in Poland, is that we're using party list systems. So instead of voting for parties, you're simply, instead of voting for specific candidates, you simply vote for parties. So you say, I want party this and that to be in the parliament. And then it is kind of really easy to make proportional result, but voters do not really have influence to who gets into the parliament. So a typical candidate can say, well, I somehow like my party leader more than I like my voters, because he's the one who puts me high in the party list, and that's how I get into the parliament. So this is, again, this system is proportional. It is used in many countries, but somehow we want something better. We want a setting where that will be proportional, and we will still be able to actually vote on specific people that we can put in the committee. Yes?
Yeah, so just 7 years,
Mm-hmm.
no, actually 8 years ago in St. Petersburg, we had maybe this is what you are heading to. So it is a combination of both.
Mm-hmm.
The size of the list is determined by the overall share of the party, but the ranking is determined by individual results of each
Sure.
party.
Yeah, so Poland has somehow a similar system as well. But it's still, the problem is actually not that the system allows you to do what you want, but most voters actually vote for number 1 of a given party.
No, so sorry. The candidates run by themselves in each district.
Okay.
Right. So you have to vote for this candidate.
Okay.
But whether he gets in or not depends on the party result and his standing in the party.
Yes. So this is pretty much what Poland uses. The problem is that most voters will simply say, okay, I like this party. I look at their list, their number 1 is this guy, I will vote for him.
Okay.
At least that's what happens in Poland.
City elections, this is not the case because they don't know these number 1s.
Okay, sure. So so at least the way the vote looks in Poland is that there's a big sheet of paper, says party this and that, number 1, 2, 3, 4, 5, 6, and you put a cross. So
you only see your own guy from your district, although you can vote for him but it doesn't guarantee
Sure. Okay, sure. So, of course, yes.
Could you define proportionality again?
Oh, no.
No?
No, because it's a whole research area. So it's an intuitive notion.
Okay.
So, well, I'm simply saying that a candidate, so essentially, if there's intense support for candidates of a given type, then more of them should get into the parliament or into the committee. If there's less support, there should be less of them, and you should observe some sort of proportionality. But in fact, if I was able to define what proportionality really means, then I would say, okay, I'm done with the voting. Because, okay, give me your votes, I will apply the definition of proportionality, optimize the solution, and that's it. So there's absolutely not a single definition of what proportionality is. In the same sense as there was not really a definition of what's diversity or what's individual excellence. So you somehow, these are convenient thought mechanisms, but actually you have to come up with somehow your understanding of this through various formal grounds. And we will see several approaches. Okay, so the first step is that we'll try to seek proportionality with ordinal preferences, so our basic setting. One thing you can do is run a single non-transferable vote rule, SNTV. Select K candidates with the highest plurality scores. So here, again, we have a preference profile, and green lady is often first, so she'll probably get in. Red guy is often in as well. So indeed, for committee size 2, they're both winning. It seems like a really simple system, but it's focusing a bit too much on top preferences. So, but it's actually, in some sense, it's interesting, because if we look at our experiments, there was either uniform distribution of candidates and preferences on a circle, or Gaussian, or 4 Gaussians, or a square. If we look at the histograms for SNTV, they're beautifully matching the original distributions. There is almost no bias. It's just copying them perfectly. So this seems like something that's really proportional, because if this is the proportion of support for candidates, this is the outcome that sounds good. So maybe it's a good rule after all. Except that the only reason why we're seeing that is that it's only proportional in the aggregate. So if you run 10,000 elections, then on the average the results will be proportional. But for a single election, for example, here, this was 200 points, of which 20 were selected. So you can certainly see that there are huge holes without representatives, and there's somehow this strange line that somehow gets promoted. Like here, just 2 guys in this whole quadrant, everyone else elsewhere. So, okay, so I guess it doesn't take too much effort to convince you that SNTV is not the most, the best rule for proportionality, but indeed, it's not the best, okay? So do you agree with me now? This doesn't look like the best rule for proportionality. Yeah. Okay, so indeed, let's now try to think what it means for a rule to be proportional. And in the 80s, there was a philosopher, Michael Dummett, who said, okay, if we're thinking about proportionality, then maybe if there's a group of at least, L is some number, L times N over K voters, who all have the same L candidates on top, then these L candidates should be members of the winning committee. So for example, here, if you take committee of size 4, so N, we have 8 voters, 8 over 4 is 2, but we're taking L equal to 2 as well. So there is a group that would feel it's good to choose red and the green. And somehow Dummett's idea is that a group of N over K voters is somehow large enough that it deserves a representative. If the group is larger than that by factor of L and they agree on who would be their L representatives, they deserve that, okay? So this is actually somehow addressing your question, how you could define proportionality. So this is one approach. You could say this means proportionality if you can satisfy this property. And it turned out that STV, not SNTV, but STV rule actually satisfies very closely a very related similar property. And if we look at STV, either you remember how, yes?
Why do you use this David's quota? Because if you consider single winner elections, it's like
So okay.
If you want true quota, we need n divided by k.
So that's in fact true. It's true that you could simply modify to use the n over k plus 1. Why not? You definitely could. You would get more or less the same definition, just slightly different. So I would say there's some freedom in this. So apparently Damet was thinking of n over k, or at least that's what we got from his works. But yes, you could change it too.
Yeah, I mean, maybe it is easier in technical computations.
I think it's in some sense, whenever people have this choice, if they don't think so, n over k just looks nicer. If you think carefully, then Drup quota can often be better. So this n over k plus 1. But in this case, this started with n over k, so that's what we stayed with. STV seems to satisfy it. So just to recall how STV works in this multi-winner setting. So here you actually have an STV based on this Hare quota, or this n over k. So here we have 8 voters. I think we're choosing committee of size 2. Yes, committee of size 2. And we're looking if there's a candidate who has n over k in this case. So we're using STV with n over k quota. So with 4 first place votes. And indeed, this is the green lady. So she's in the election and she's being removed from the election, from the consideration. Now look, there was also a voter who liked her best, who is not removed, but she is removed from his vote. Okay, now, yes?
It's a hard question how to choose.
Exactly, there's no good answer. There's simply no good answer.
How, you know, I always was thinking about when we have a computer, we can use fractional votes. Yes?
Yeah, and we can.
But 100 years ago, without a computer,
yes.
How did they?
So the answer is simple. 100 years ago, they did not use fractional votes.
Yeah.
And
how did they do it?
So for example, I mean, one solution which you would not use in political elections is simply choose randomly. You could try to find some sort of tie-breaking mechanisms, and that's exactly why STV rules are difficult to specify, because there's lots of complicated rules saying who you should delete and why and how it proceeds. So I will not give you the answer. So I don't know how they did 100 years ago, but it is complicated. Okay, but we remove them. Now red guy has 2 votes, orange and blue have 1. So first we have to delete pink because she has nothing. Then we can delete either blue or orange. We delete orange. We're left with blue versus red. By random choice, we delete and we get a red guy. So this is how STV proceeds. We've seen it many times. And again, these are the pictures computed for STV. So again, they look beautifully. They look just like SNTV. What problems do you envision after I show you the actual results?
Again, aggregation.
Huh?
This is the result of aggregation.
No. There are no problems. It just works. So if you remember, we have seen how you increase the committee size for STV at the very beginning today. It was always very nice, and indeed it always seems to be following the distribution of the voters. In fact, in very recent results, I was somehow trying to understand how STV performs, and it turns. So what I will say now is very hard. I don't even understand it well myself currently, but essentially the results that we got is that the fact that STV mimics exactly the distribution of the voters is apparently something different from proportionality. So it seems that we can define in a reasonable way the notion of proportionality so that we don't actually get mimicking of the voters. I cannot explain it just yet, so we have to proceed a bit, and then I will be maybe able to somehow find something. Okay. But in any way, STV is generally believed to be a good solution for proportionality. The problem is that, as I told you, it's non-monotonic. So if you have a profile like that, with 10 voters, 10, 9, 1, 10, and if we do the tie breaking so that green is ahead of orange, ahead of red, then first here red has 10 votes, orange has 9, 10 votes, and green lady has 10 votes. So red is last in the tie-breaking order, which means he is removed. And now we have 10 votes for and 20 votes for green, so green is elected. But now, let's say that green improves her position. If she improves her position, then now orange has to be removed in the first step. So we're red, but now red has 19 and green has 11 votes, so the red wins. So even though green improved her position, she can actually lose. So I mentioned that we'll see this example, and here it is. Okay. So what else can we do? If somehow we care about monotonicity, then there is actually not much we can do, because many of these rules are losing various types of monotonicity. But we can try to seek a different rule. There's a rule called Monroe, which somehow we associate with the idea of solid coalitions, which, as we will see, is actually incorrect. But the idea of the solid coalitions property is to say a rule is proportional if, assuming that n over k voters rank some candidate on top, then this candidate belongs to the winning committee. So here, so this is less than Dammett's proportionality. It is Dammett's proportionality for L equals 1. And in this case, the green lady is on top 4 times, so she should be in the winning committee. And so we can define a variant of Chamberlain-Courant rule in such a way that it maintains, that it tries to follow this idea of solid coalitions. So given a committee, a Chamberlain-Courant would simply assign the best member to each of the voters. Here, under Monroe rule, we can assign each voter one of these two guys, but in such a way that every candidate is assigned to exactly n over k voters. So in this case, the green lady has to go to half, and the red guy has to go to half. So for example, like this, red, 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 so 4 guys, 4 guys. Chamberlain-Courant would, of course, would do something like this, but this would not be balanced. So even though it would be a better score, it would be illegal under Monroe rule. Okay, so Monroe rule is Chamberlain-Courant's rule with the requirement that every candidate, every committee member represents the same number of candidates. So it seems like something that should be proportional, right? And the committee with the best assignment is, of course, winning. Strangely enough, Monroe rule fails the solid coalitions property. Here's more or less a counterexample. The reason is that if we have committee size 3, we have these 3 voters with red guys on top and the others, then strong solid coalitions would require us to choose the red guy, but then we have only 2 left for the bottom voters, and someone would be left with terrible choice. But if we choose green, pink, and orange, then these are quite satisfied as well. Okay. Another problem with Monroe rule is that just like Chamberlain-Courant, it is NP hard to solve. But even worse than Chamberlain-Courant, Chamberlain-Courant was polynomial time for single peak preferences. Here it seems to not be the case. There is a paper by Betzer, Slinko, Ullman that suggests, it doesn't actually prove exactly that this is NP hard, but it shows that if you play with the scoring function a bit, it becomes NP hard. For single crossing preferences, which we have seen already so far, where there is a polynomial time algorithm for Chamberlain-Courant, we also have NP hardness proof this is some picture that captures the main idea of the proof. It's not very meaningful at this point. But the problem is that Monroe rule is somehow quite difficult to compute. That's why we have introduced greedy Monroe. I always wonder what would happen if I was once giving this lecture and so Monroe was a guy. And if he was in the room and I say, and now I introduce greedy Monroe. But luckily he's not here. Yeah. So the way this algorithm works is that our goal, we find a group of n over k voters and a candidate C, such that the score of the voters from C is maximal. And we remove this candidate and the voters from the election. So in this case, for k equal 2, we would first find the green candidate, because she's ranked first by n over k voters. We would put her into the committee and remove from the election. Now we would find another candidate, for example, blue, and we would put him into the election, we would remove these votes and we would be done. So this is how the algorithm proceeds.
Sorry, how do we pick up blue guy?
So the score of the blue guy is 2 plus 1, that's 3. Here plus 2, 5, it's 9. The orange guy, for example, has 0, 6. Okay. The red guy, it's 8, 0, 9 as well, so tie. Yeah. So we simply find someone who we can give highest score from n over k voters. Okay? And clearly, by the very definition, greedy Monroe has to satisfy the solid coalitions property, and it does. And it is quite a good approximation algorithm. So I guess I have a mild suspicion that you do not want to see yet another analysis of an approximation algorithm. But I would need it confirmed by simply saying someone, yes, we can move on.
Yes.
So I see you can take the responsibility. So it's actually not so difficult. It's also a pigeonhole principle thing with some equations. But in the end, we're assuming we can get a k minus 1 over 2m minus 1. So essentially a relatively good approximation guarantee. So if we run Monroe on Polish parliamentary elections, where the committee size is 460, and this actually increased recently to 8,000, but not on the last, but on the previous elections it was 6,000, then we get 96% approximation ratio. Of course, you can ask yourself, how can we rank 6,000 candidates? And that's a bit undoable. But in fact, if everyone reports only some top percent of the preferences, we still get quite high approximation ratio. So for example, here if we report 10%, then for 300 candidates and 1,000 candidates, we already achieve 80% approximation ratio. The problem is that 10% of 1,000 is still 100. It's still a lot. So yes, on theoretical grounds, that's an improvement. In practical, still not very usable. But the nice thing is comparison of Monroe and greedy Monroe in terms of our pictures. And it actually, so the funny thing, so Monroe was the original rule. It was defined, I think, in the 90s. And it was NP hard to compute, but it didn't have the solid coalitions property. And here, apparently, the greedy Monroe, which is polynomial time computable and has the nicer properties, is actually giving us slightly nicer diagrams. Because here, again, we see this line of lower support for non-extreme extremists, and here it is much less pronounced. Okay, and there's lots of papers on approximability of Monroe rule, but this is all that I have to say for ordinal preferences with end proportionality. So the next thing that comes are approval preferences. And this is much more realistic because it's, as I told you, it's easier to assume I can have approval sets rather than ordinal preferences. And here we can essentially use this idea of of damage proportionality and of solid coalitions in a similar way, but somehow much more successfully. So we will say that an L cohesive group of voters is a group of at least L times N over K voters who all approve the same L candidates. Of course, maybe they can approve some others as well. So for committee size 2, this is a group of 1 cohesive voters because they have a common approved candidate. If we take committee size 4 and L equal to 2, this is still an L cohesive group because they all agree on 2 candidates. Okay? And now there is a notion called justified representation, which says a committee provides justified representation if in each one cohesive group there is at least one voter who approves a committee member. This seems like a silly phrasing. It is, in some sense, it is a stability notion. Because what it says is that if we have a cohesive group, then at least one of the guys has to approve a committee member. Here you can see that actually all of them approve a committee member. But if you had a cohesive group where nobody approved a committee member, then you could say, okay, these guys are going to revolt. And they can go to the authorities and say, there's enough of us, we deserve representation. But if at least one of them has a committee member, then they wouldn't have enough. So, yes?
Could you roll back when you include the green and red guy? Like, the red guy doesn't matter actually, to be a cohesive group of voters, right?
So to be, I don't follow.
So this is a cohesive group of
Yeah, but for justified, we're looking at the one cohesive.
I'm looking at this for it. So if you say like K4 and now equal 2, it doesn't really matter who is standing on the second.
Well, I mean, these are approval sets, so this is not first, second, of course. They're both equally approved.
Okay.
By N over K is now 8 over 4, it's 2.
Oh, you mean approves the same candidates, it's in summon?
Yes. Okay. So the same L. So the fact that they have some other guys doesn't matter.
Okay.
Mm-hmm. Okay.
Could you repeat this one?
Okay. So we're saying that a committee provides justified representation if for each one cohesive group there is a voter who approves a committee member. Because if there was a cohesive group, so for example, if we look at a situation like this, committee of this guy and so light blue and orange lady, none of these guys approves of anyone in this committee. So they can somehow they have a justified claim that they can go to the authorities and say, we deserve to be represented. So we want this to not happen. We want that always there's a committee that at least one of them has an approved candidate, and maybe this is just this voter approved scheme, or maybe this is the common approved one, doesn't matter. Okay. Interestingly, for every approval election, there exists a committee that provides justified representation. It is a relatively simple proof that shows this. So we can in fact do it. So my claim is that in every approval election, there is a committee, there is a JR, Justified Representation Committee. Okay? Proof is very simple. So it's enough to take the following algorithm. So in the first step, this is actually a greedy algorithm for approval-based Chamberlain Courant. In the first step, you choose the candidate that is approved by the most voters. Okay? In the second step, so you remove his voters. In the second step, you choose the candidate who still is approved by most of the remaining voters, remove them, and so on. Okay, this is the process, right? Now imagine that after this process, there is a cohesive group, there is a one cohesive group. So after the process, there is more or equal n over k voters who approve some candidate C. Okay? This is after k steps of the process I described. But in every step, since there was n over k voters who are approving some candidate C, it means that in every step of the process, I must have chosen a candidate who is approved by at least n over k voters, right? Because if I chose fewer, then I would have chosen C instead. Agreed? Okay? But if in k steps, in every of the k steps, I chose at least n over k voters, then after k steps, I must have removed n voters already, and this is a contradiction, because there can't be n over k voters left to form a cohesive group. Okay, so in every election, every approval election contains a committee with justified representation. And in fact, we can achieve even more. If we use the PAV rule, the proportional approval voting rule, this was this committee where the committee was a sum of harmonic numbers, then the rule proceeds as follows. If we have a committee of green, red, and blue, then the score from voter 1, he has only 2 representatives, is 1 plus half. From V2 is again 1 plus half, here 1 plus half plus third, and so on. We get score 8, 5/6. So this is, yes?
Is this true? Log with n divided by k plus 1.
I think it's still true, because you still exceed the limit. Okay, so this is how the PAV rule works. A committee with the highest total score wins the election. And so actually, why did I show you proportional approval voting? Because it is quite strongly believed that this is the actual proportional rule. So STV is one kind of proportionality, PAV is the other. And amazingly, PAV on a circle actually chooses a smaller circle. It focuses. It removes, so somehow it's proportional, but it bans the extremists. On a square, again, proportional, but it removes the extremists. And this is also true in the other settings. There's all sorts of papers about hardness of computing this PAV rule. But the amazing property that PAV has, and that somehow makes it seem proportional, is that it has extended justified representation. So remember, an L cohesive group of voters is a group of at least L times n over k voters who all approve the same L candidates. And a committee provides extended justified representation if in each L cohesive group there is a voter who approves at least L committee members. So here, if we have this cohesive group, 2 cohesive group for committee size 4, then one of these voters has to approve 2 committee members. Okay, so for example, a committee with red and green would be okay. The committee with orange and red would be fine. Pink and red would be fine, or blue and this strange guy would be fine. But one of them has to have these L committee members, again as a form of stability, I would say. And amazingly, PAV satisfies this property. And one of you asked, why in the world does PAV use this sequence? And the thing is that if we use any other sequence, it no longer satisfies extended justified representation. So this is somehow really the sequence of proportionality. And there's we're somehow slowly coming to the end of the time that we have. So I will skip through some things. I will also, I will show you a sequential version of PAV. So also trying to convince you that this harmonic sequence is actually something that leads to proportionality. So the idea is that we would like to use, so we try to use these multi-winner rules, but in a party setting. So we have party A, party B, party C. There are 60 votes for party A, 30 votes for party B, 10 votes for party C. Now we're imagining if we're choosing a committee of size 10, then we fill in each of the parties with 10 candidates. And we're saying that every voter who actually voted for party A, in fact, approves these 10 candidates. And now we're using what I will call sequential PAV rule, which is like this greedy approximation of PAV rule. So I choose committee members one by one, so that the score increases most. So if I choose a candidate from party A, there's 60 votes, each worth 1 point. It's 60, it's better than 30 or 10. So I include blue party A member in the committee. And now, under the harmonic sequence, the value of voters, of blue voters, changes to half. So now we have a 30-30 tie. So I will still take a blue guy because just like that, but it changes to 1/3. And then the green party wins. It becomes half. So now I take blue. We change to quarter. We still have a tie, and we go on like this. And in the last 3 steps, I have an all-way tie. So I will choose red, decrease, choose green, decrease, choose red. And now I have a committee of 10 guys, 1, 2, 3, 4, 5, 6, exactly proportional to the number of voters. 1, 2, 3, exactly proportional to the number of voters. 1, exactly proportional to the number of voters. So indeed, there is some magic in this harmonic number. It is possible to prove it formally. If you look for a paper by Haris Aziz and others with justified representation in title, it will be explained. It was published in Social Choice and Welfare. So indeed, we achieve proportionality. And if we were using, say, Chamberlain Courant, then we would, for example, if we had 60 votes like this, 30 like this, 10 like this, and 1 vote for each of those, we would get a very diverse committee, but not very proportional. Okay. And I think this is a good time to stop the actual lecture and to actually have some sort of summary. So we had multi-winner voting. So multi-winner voting. We have our 3 goals of individual excellence, diversity, and proportionality. And there are various rules and axioms that fit each scenario. So for individual excellence, we would have committee monotonicity, maybe Gerlain stability, maybe some other sets of axioms and rules such as K-Borda, maybe K-Copeland, and so on. And this is essentially, I would say, this is the world of polynomial time computability. Here, usually, we can compute things efficiently. Then we have diversity, and here we had on the axioms front, we had narrow top and top member monotonicity, top member monotonicity. I guess I'm not so used to writing with chalk, but and essentially, more or less, the only choice was Chamberlain-Courant rule. And here we have NP hardness, but we can deal with it most of the time. And finally, proportionality. This is somehow, in some sense, there is the largest number of works in economics was on proportionalities of various kinds. Now with this multi-winner setting, this is becoming more and more charted territory, but there's lots of ideas. There's justified representation, there's Dammit, no. Among rules, there is STV, there is PAV, there is Monroe. Monroe is actually friends with Chamberlain-Courant, and PAV is not. There's actually quite a bunch of rules that try to achieve some level of proportionality. So I would say there's probably currently in this research, most work is somehow trying to understand what proportionality is and how it relates to other things. And to move to the final slide, well, thank you. But also, there's one thing I would like to mention. So all the pictures that you have seen, all the blue pictures that you have seen throughout this talk, they were generated using software available on GitHub. So this was a Python library that me and my colleagues have developed. It has some bugs, but not many, as far as we know. But we're currently working on version 2. But anyway, if anyone wants to actually repeat these experiments and try them on their own, it's completely feasible. And there's one thing that I'm absolutely proud in this library. There is a manual. There's actually a manual that tells you what to do to achieve the effects we have done, with actual commands to run. Okay, so thank you very much, and have a good evening.